Hey everyone, welcome to The Explainer. Today, we're unpacking a concept you see literally every single day in research papers and lab reports, standard deviation. But we're not going to just read abstract textbook formulas, no way. Instead, we're taking a logical, step-by-step clinical approach to discover exactly why this math exists and how it solves a very real problem when we're dealing with patient data.
Here's our roadmap for today. We'll start with why we measure data spread, find the clinical center, tackle the dreaded zero problem, square things to find variance, returns clinical unit, and finally interpret the result.
All right, Section 1. Why measure data spread? The clinical need for context. Let's ground this in reality, right? As medical students and junior doctors, you are drowning in patient data daily. Heart rates, blood pressures, lab panels, the whole shebang. But knowing just the average of those numbers, it's really not enough. You need context. You absolutely must know how reliably consistent those numbers are. And that's exactly where standard deviation gives us this crucial clinical context. It tells us if our patient's lab results are tightly clustered around a baseline, which is a small SD, or if they're just wildly fluctuating, giving us a large SD. It's literally the difference between a stable patient and one whose vitals are bouncing all over the monitor.
Imagine you're tracking a patient's consecutive lab values over your shift, and you get 12, 13, 14, 15, and 16. Think about what that spread actually looks like. We have our lowest value at 12, our highest at 16, and they're all just kind of distributed around that middle area.
Moving on to Section 2, finding the clinical center, or establishing the mean. Before we can figure out how far our data is spreading, we logically need an anchor point, right? Where is it spreading from? We calculate the mean to find this exact center point. We just add our 5 values up, 12, plus 13, plus 14, plus 15, plus 16, and divide by our total number of 5 observations. That gives us a mean of 14. This step is absolutely vital because standard deviation is, at its core, simply a measure of how far our observations deviate from this exact center point of 14.
Section 3. The zero problem. This is a classic mathematical trap.
So you want to know the spread? The logical first step is to look at the differences from our mean of 14, which gives us a list of simple deviations. 12 is 2 below the mean, so that's -2. 13 is -1, 14 is right on the mean, giving us 0, 15 is +1, and 16 is +2. We now have our list of negative and positive deviations.
But wait, at this point, we just have a list of numbers. We don't have a single summary number describing the spread. So which one is the true standard deviation? Is it the -2? The +1? We obviously can't just pick one at random. So naturally, you might be wondering what happens if we simply average all these deviations together to find a typical spread.
Well, if we take -2, -1, 0, +1, and +2, and we average them, we get exactly 0.
And that right there brilliantly illustrates the zero problem. Because some values are below the mean and some are above, the positive and negative deviations perfectly cancel each other out. And this incorrectly suggests to us that there is zero variability in the data, even though we know for an absolute fact our patients' numbers are fluctuating from 12 to 16. The simple math completely fails us here by masking the very real clinical variability we know is present.
Section 4. Squaring to find variance and solving that pesky negative sign issue. To fix this mathematical illusion, we literally have to mathematically strip away those negative signs, so the distances don't just destroy each other when we try to combine them. The tool for this? Squaring. By squaring each individual deviation, a -2 multiplied by a -2 becomes a +4. A -1 becomes a +1, 0 stays 0, +1 becomes 1, and +2 becomes 4. If we add up these new squared deviations, we get a total sum of 10.
Squaring is actually a super elegant fix. First, it forces every deviation to be positive, stopping them from canceling each other out. But secondly, and this is a real game changer for clinical data, it gives greater weight to observations that are farther from the mean. A deviation of 2 becomes a 4. A deviation of 3 becomes a 9. It naturally highlights those larger, potentially more clinically concerning outliers. Now we need to average out our sum of squared deviations. But instead of dividing our sum of 10 by our total sample size of 5, we divide by n-1, meaning we divide by 4.
Why n-1? This is known as Bessel's correction, and it deals with degrees of freedom. Now, without getting bogged down in heavy math jargon, think of it this way. We're looking at a limited sample of patient data, not the entire hypothetical population of every lab result this patient will ever have. Our small sample tends to slightly underestimate the true, wild variability of the real world. By dividing by a slightly smaller number, 4 instead of 5, it bumps our final answer up just a tiny bit. This minor adjustment acts as a safety buffer, ensuring our math doesn't artificially underestimate the true variability.
So we take our sum of squared deviations, which is 10, divide it by our degrees of freedom, which is 4, and we get 2.5. We call this number our variance.
Section 5. Returning to clinical units because we need to make sense of the math.
While a variance of 2.5 is mathematically flawless, it poses a highly practical problem on the wards. Because we squared everything earlier to get rid of the negative signs, our units are still squared. Imagine looking at a hemoglobin result and telling your attending physician the variance is 2.5 squared grams per square deciliter. They'd look at you like you're crazy, because nobody thinks about patient data in squared units. It is entirely meaningless for practical interpretation.
We've got to return to reality. To basically undo the squaring we did earlier and bring our number back to the original units of our patient's labs, we just take the square root of the variance. The square root of 2.5 leaves us with a very usable 1.58. And that number, my friends, is exactly our standard deviation. Finally, Section 6, interpreting the final result, the actual clinical takeaway. Now that we've survived reverse engineering the formula, here is the payoff. This is exactly how you'll see data presented in clinical research papers, pharmacological trials, and lab reports. Mean equals 14 plus or minus 1.58. It's no longer just a cryptic string of symbols. It simply and intuitively means our patient's center point is 14, and you can expect their individual results, on average, to naturally fluctuate about 1.58 points in either direction. It gives you an immediate, intuitive sense of the clinical spread. You aren't just reading some abstract formula anymore. You're looking at an elegant, mathematical solution to a very real clinical problem. Squaring to fix the zero problem, dividing by n-1 to respect the sample limits, and square rooting to get right back to the patient's bedside. Which makes me wonder, now that you know the hidden story behind these numbers, how will this deeper understanding change the way you read and trust the data spread in your next clinical trial paper? Keep that in mind next time you're rounding on a patient. Thanks for joining me on this explainer.